We are now ready to solve this problem with a hypothesis test. Harris Health Systems, remember they claimed that 87% of their employees get a flu shot. We took a sample of 300 to found that 249 said they received their flu shot. We want to test this with an hypothesis test, and we're going to assume a level of significance of 0.01. In this particular case, remember the claim here, they are claiming that the proportion of employees that get their flu shot is equal to 0.87. So the claim is that the proportion is equal to 0.87. Remember when we're writing our null and alternative, the null and the alternative hypothesis, the null will always have equal to, and the hypothesis, the alternative hypothesis, will have something that's mutually exclusive from that null hypothesis. Since the proportion that's in question here is 0.87, that's the value that's going to be a part of both our null and alternative. And remember, the null is always at its equal to, and the alternative is either going to be greater than, less than, or not equal to. And in this case, they're not saying that we want to test that less employees did or more employees did. It's just we want to test that exactly 87% or approximately 87%. So we're just going to have alternative be that it's not equal to. Notice these are mutually exclusive. Since our not equal to sign is in our population, or our population parameter, and our alternative is not equal to, this is a two-tailed test. A two-tailed test, which means when we draw and label our bell curve, it's going to have two tails, two rejection regions. So let's first solve with the critical value approach, and then we'll go through the p-value approach. Let's draw and label the bell curve. We're going to label the rejection or cutoff, and that cutoff we're also going to find our critical value. We'll find our test statistic to see if it's in the critical value, critical region, and then we'll state the conclusion. So let's draw and label our bell curve. Here we have our bell curve, and the population parameter in question is 0.87, so that's going to be in the middle. We have a two-tailed test because it's not equal to, so I'm going to draw my two tails. We are testing with a level of significance of 0.01. So alpha is 0.01. So that means the area in each tail, if I were to, since I have two tails, I'm going to split this up. I'm going to have 0.005 in each tail. So here's 0.005, here's 0.005. And what I need to find is a critical value. The critical value is going to be the z-score that has 0.005 to the right of it. So let's get out our z-table to look for the z-score that has 0.005 to the right. Okay, so in our z-score chart, we're looking for a z-score that has 0.005 to the right. So if we go down here, remember these are going to be the common critical values here. If we look up here, and actually let's go back to the picture. If there's 0.005 to the right, that means there's 0.995 to the left. So if we look up 0.995 exactly, it's going to be right here. So our critical value is going to be 2.575. So this is going to be our critical value will be equal to 2.575, which means this one's going to be negative 2.575. This is the value, or the z-score, and we know that if there's 0.005 to the left of negative 2.575 and 0.005 to the right of 2.575, then this is going to, in the middle, account for 99%. So this is similar to our z-scores for our 99% confidence interval. What we're going to do, why is this important? Because we need to calculate the test statistic. The test statistic is going to be relative to our sample, and then we're going to find, given the sample, does that test statistic for the sample fall into one of these rejection regions? Because that's what these are. When we draw these tails, these are the rejection regions. So the formula for the test statistic, we're going to take our p-hat, which is our point estimate. We're going to find out how far away is it from our population, our assumed to be population parameter. and then we're going to divide that by the standard error. This is just like when we calculated a z-score. We subtracted to find the value and divided by the number of standard deviations. But now we're figuring out how far is that point estimate, that sample proportion, how far is that from the actual hypothesized proportion, and then we're going to divide by our, in this case, our standard error, which is p times q divided by n. So let's plug these values in. P hat, in this case, is our sample, and that's going to be, we actually have to find that, right? Our sample proportion is 249 divided by 300. So our p hat, in this case, is going to be, as we found before, 0.83. Our regular p-value, in this case our hypothesized, is 0.87, which means our test statistic q, or excuse me, our q, 1 minus this, is going to be 0.13. And our value of n, in this case the number of our sample, was 300. Okay, so now we have all the values we need to find this test statistic. P hat minus p, this is going to be 0.83 minus 0.87. Then we're going to divide by the square root of p hat times q hat. So p hat, or excuse me, the p times q, regular p and q, these were the population, not the sample, so 0.87 times 0.13 divided by n, which in this case was 300, negative 0.04. So I did everything on the inside, then I took the square root of that. I get approximately 0.01942. I get approximately negative 2.06. Approximately 2.06. So what is this? What did I just find? What I just found, again, is the test statistic. If I take this test statistic and I plot it on my bell curve, here's negative 2.575. Negative 2.06, that's going to be right here, right? It's not more negative than 2.575, so that's going to be right here. I am not in the rejection region. I'm going to fail to reject. Fail to reject the null hypothesis. The reason why is because my test statistic does not fall into the rejection region. A quick summary: I drew the bell curve and I labeled the hypothesized proportion in the middle. I knew I was working with the two-tailed test because this is a not equal to, so I labeled my two tails. Given my level of significance of 0.01, I know the area in each of those tails, which means I can find the critical value. So I found the critical value, so that is going to be the cutoff from the rejection regions, in this case 2 rejection regions, from the fail to reject region. I knew I was working with z-scores because I know that the sampling distribution is going to be normal. All right, when we get into means, we're going to be using the student t distribution. Then I calculated the test statistic. This is the formula for the test statistic for a proportion. I found that with a sample proportion of 0.83, that's associated in this example with a test statistic of negative 2.06, which is not in those rejection regions, meaning it's not so far away from the mean. I mean, it's negative 2.06 away, so it's definitely some amount away, but it's not too far away where it's unheard of given this level of significance of 0.01. So if it was beyond negative 2.575, like negative 3 or negative 4 or negative 5, then in that case we would reject. But it's not, in this case, significant. So I would fail to reject the null hypothesis. We don't say there's evidence to support the null hypothesis. We wouldn't say that. We would just say there's not enough evidence to reject this. Given our level of significance, we can't reject the null. The final thing I'm going to do here is to calculate the p-value. I should, after calculating the p-value, I better get a value greater than 0.01, right? Remember the p-value, we're going to calculate the p-value, and then we're going to compare that to, so this is a symbol for comparing, depending on it's greater than or less than, the level of significance. So the level of significance. Now, if our p-value is less than our level of significance, then we reject. If it's greater than, then we fail to reject. So let's go ahead and calculate the p-value, and we're going to use StatCrunch for this. So I'm going to open up StatCrunch, and I'm going to type in the information. So here's StatCrunch. I'm going to go to Stat. I'm calculating a proportion stat. It is one sample with summary. I know that my number of successes in this case was 249 out of 300 observations. That's my sample information. I'm not doing a confidence interval, I'm performing a hypothesis test where the null hypothesis is that the hypothesized proportion is 0.87 versus the alternative that it's not equal to. From there, you just hit compute, and here we go. Gives us the proportion, summarizes our sample values, gives us the sample proportion, our standard error, which in that case was our denominator of the test statistic formula. Here is the test statistic, negative 2.06, a little bit more because they have the ability. And then finally our p-value is 0.0349. 0.034 or 0.0394, I think. That's how good my memory is. There we go, 394. So our p-value in this case, and our level of significance, which is 0.01, since our p-value is greater than our level of significance, we fail to reject. Now, just for theoretical purposes, what if my level of significance was not 0.01, but our level of significance was 0.05? Well, in this case, if we use the p-value approach, our level of significance is 0.05, our p-value is less than that. So we would actually, in that case, reject the null hypothesis. So it really depends on how you are labeling and how you are defining what's significant. If we want to be really sure that it's not equal to 0.87, then we're going to have a lower level of significance. We want to define significance as being, or something being significant as having a 1% chance of occurring by chance. So in this case, here we have our level of significance with a 0.01. We did not reject.